All right. Last time we were doing this problem, we kind of got stuck. Not stuck, but it was very tedious, and so I have to say that the problem like this won't show up in a quiz or an exam. I mean, maybe a homework, but it was a little too tedious in terms of the calculations that need to be done. So what I wanted to do today was I wanted to finish this problem off, and what I did was I had to ask Mathematica for help. And so I just punched in some values, and if you want to look through it, copy it, or you can just look at the notes, that's fine. But what we'll do is we'll take a couple of problems from your homework set, since you seem to have a lot of homework that's going to be due on Sunday. So we'll try to take a couple of those problems to alleviate some of the homework problems that you'll be thinking about. And then we'll jump to the next section by just doing problems from your homework again. All right. So the problem was this x squared plus y squared times e to the y squared minus x squared. And so already from the beginning, I thought this is going to be a lot of work, because it's going to be a product rule for the first derivative, and then the second order partials will have more product rules, and it'll be tough to keep track of. And so I just had Mathematica do it for me. And we have a set of critical points, which is what we got last time. So we got 0, 0, and then when we did some sort of substitution, we got negative 1, 0, and positive 1, 0. So here are our three critical points. Now, the matching up the critical points is an important aspect of doing this. I think it's important for us to be able to practice finding the critical points by setting each derivative equal to 0 and knowing what it means to have both fx and fy equal to 0 at the same time. And I'm hoping with a few more examples we'll get used to identifying critical points clear. For now, this is what we have. We have 3 points to check. And so this is where we got stuck last time. We took the second order partial derivatives. So these are the second order partial derivatives in general, simplified. So we have partial derivative with respect to x twice, with respect to y twice, and then the mixed second order partial fxy or fyx, which will yield the same result. And what we need to do is we need to find each of these second order partial derivatives evaluated at 0, 0. That's one of the points that we have. And so fxx at 0, 0 is 2, and fyy at 0, 0 is 2, and fxy at 0, 0 is 0. So our d in this case, to be more specific, our discriminant evaluated at 0, 0 is going to be 2 times 2 minus 0 squared. So you know where each of these are coming from. According to the discriminant, it's fxx times fyy minus fxy quantity squared. But we have specific values to put in. And so from here, we get that this is equal to 4. Not that the value is equal. More importantly, we have to check if it's bigger than 0. So if it's bigger than 0, we have to check one more thing, and that is to check fxx. And again, not that the value is important. What is important is that this is bigger than 0. And so when it's bigger than 0, we see that it's concave up, or we see that we have a local min. And the local minimum is at 0, 0. Okay, any questions? All right, the next one, we're doing the fxx at negative 1, 0. So this is at negative 1, 0. And the discriminant is equal to fxx times fyy minus fxy squared. And so we get negative 16 over e squared. And again, not important what this value is, but what is important is that this is less than 0. It's a negative number. And so at this point, you can already stop and say we have a saddle point. At negative 1 comma 0. Okay, so remember, if the discriminant is less than 0, we don't have to check anything else. We just conclude that it's a saddle point. And then finally, we got the discriminant at 1 comma 0. Should do this in a different color. So the discriminant at 1 comma 0 is the same thing as the previous one, negative 4 over e times 4 over e minus 0 squared, which is equal to negative 16 over e squared, which is less than 0, and that gives you another saddle point. Yeah, you can have multiple saddle points. You could have multiple local max and mins also.
It's not like just a line, it's a plane, so it can have a lot of bumps, right?
Yeah. Yeah. You have to look at it as an enclosed value, and you could find the z values to see which one's the highest and the lowest. And we'll talk about that. Usually we refer to finding the global max and min if we have a closed region. All right, let's take a look at a graph of this, because we can. And here's the graph.
If you look straight down, you notice does it have that little divot that
Oops, hold on. I have to rerun some of these things. So if you look at it from the top, you can see there's some strange things happening. If you look at it from the side view, you see that there's this local minimum over here. That's probably going to be at 0, 0. And then there's these indentations over here. That's neither a max nor min. We'll take a look at that a little bit more closely. So I have several shots of this, and what I did with these several shots is I focused around the critical points. So here's the overall shot. This is from x goes from -4 to 4, and y goes from -2 to 2. And that's the domain that I took, and this is the picture that we get. So let's take a look at this picture and try to guess at where some of these things are, some of these things that we're looking for. So this is probably 0, 0. And if we want to double check to put this into the original function, you get our f value, right? So our original function was x squared plus y squared times e to the y squared minus x squared. So evaluate that when x and y are both equal to 0, you have 0 times e to the 0, which is 0. And then you could do the same for these things. So these things must be the other points that we were concerned about. This is, I guess this would be +1, 0, comma. If we want the z value, The z value would be 1 e to the negative 1. So 1 over e, basically. So 1 over e, and then I think this will have the same z value. Okay? So what I did, because when I first saw this, without all this other, in Mathematica, without all this other restrictions, it kind of gives, yeah, so the z goes all the way up to 10 here, and it's hard to see those movements. So to try to look at it closer, I zoomed in to each one. So this went from, actually I meant to put 0.5. And so this focuses on the middle part right here, and clearly it's that parabolic shape, paraboloid shape. Around 0, 0. Yeah, so this is a zoom in box over here. Okay. So that's the obvious one. Let's take a look at the saddle points and, try to imagine what the saddle point actually means. So for the saddle points, I zoomed in on this one. I zoomed in around -1, and then 0, 0. I suppose I could have made this 0.5 also. So I can clearly see the saddle shape of this thing. I don't know if they're sitting around horses.
How far back? How far back? That's actually where the rest they saw horse. Well, they just said 6 maybe they didn't see.
So the whole idea behind a saddle is that there's some directions where the graph is going downward, like a downward parabola, and some directions where the graph looks like an upward parabola. So this is at x is equal to -1. Picture. So if we imagine we're zooming in here, this is a saddle that we see, and then we'll see the same thing. No, we'll see the same thing on the other side, so why don't we just pretend we took a picture of that also. So here are 2 saddle points, and this is what the picture would look like. Okay? All right, let's take a look at some of your homework now. Did I sign in? Not responding.
Can you work on just starting a little bit of that lab next to you tonight?
Well, if you made it through, then you're done. I mean,
I was just looking at it, and I just, like, you guys were so far, I was guessing numbers. Reading something.
would you rather have me do a lab or a homework problem?
Lab too. Plus, in the homework, you get to practice it.
All right, so I'll skip over the homework then. I'll do some labs. What? You said homework? Okay. Let's do homework then. Which one do we do? Which one? 1 through 5, 2 through 5. Which one should we do? 3. 3? All right. We want to find local max and mins and saddle points. Did we do something similar to this with an exponential function or something? So should we do this again, or should we try a different problem?
Let's do something different. Well, let's have cosine involved.
So who wants to do this, or move on to another one? Who wants to do this? All right, let's do it. So find the local max and mins and saddle points of the function. If you have a three-dimensional graphing software, graph with a given domain, enter your answers here. So notice that they're looking for values here. So the values that they mean is just the z values. So whatever your z value is what you put in here. The saddle point is an actual three-dimensional point. And so when you're entering these things, just be aware of what you're entering. All right, let's start by finding the critical points. So we need fx and fy. We're going to set that equal to 0. So derivative of cosine is negative sine. So 8y times sine x with a negative in front. We're going to set this equal to 0. And then I'm going to leave some space here. Fy is going to be the derivative of this with respect to y, which is 8. And then cosine x is a constant. We're going to set that equal to 0 again. So when we set that equal to 0, we get y is equal to 0, and sine x is equal to 0, which gives us x is equal to n pi. Well, I guess we're just going to go between 0 and 2 pi, so that would be x is equal to 0, pi, and 2 pi. And on the other hand, when fy is equal to 0, we have cosine of x is equal to 0, so that's x is equal to pi over 2 and 3 pi over 2. Between 0 and 2 pi, that's the only time it's equal to 0. So what we need to do is, this is where we need to have both of them equal to 0. So when x is equal to 0, or when x is equal to pi over 2, and x can't be equal to 0 at the same time, right? So we can say that we can't cross these things, cross-contaminate, cross-match. We can't match. We can't match up the zeros and we can't match the pi over 2, x is equal to pi over 2, and x equal to 0 at the same time. So what we want is we want to figure out when this thing is equal to 0. So fx is equal to 0 and when y is equal to 0. At the same time, fy is equal to 0 when x is equal to these 2 points. So that means x is equal to 0 and x is equal to pi over 2 can't happen at the same time. Y is equal to 0 and x is equal to pi over 2 can happen at the same time. And so that's the pairing that we're going to get. So our critical points are going to be pi over 2 comma 0 and 3 pi over 2 comma 0. So those are our critical points. Yeah, and then we have to figure out their local max or mins. Now, before we go on, I guess this whole idea about cross-matching and making sure that you got both of them equal to 0, I don't know if this will be helpful, and this will require you to be able to graph things quickly off the top of your head or on paper. But what I could do is I can find all these values where fx equal to 0, that's y is equal to 0, x is equal to 0, x is equal to pi over 2, or just pi, and then x is equal to 2 pi. And then what I would do here in this case is set all these to be the same color graphs. And so the red graphs will be the graphs where fx is equal to 0. Now fy is equal to 0, I'll make that a different color. And xy is equal to 0 and x is equal to pi over 2. And x is equal to 3 pi over 2. And so what I would do here in this case, you can't see x is equal, you can't see y is equal to 0. That's too bad. I don't know if I can. I don't think this will work. No. Thickness? No. That didn't work. Anyways, the idea is that the places where the red and the blue intersect would be the places that I would be interested in. And unfortunately, you can't see when y is equal to 0. That's the x-axis in red. And so that would intersect here and here. So we'll see if we can come up with a better example later. All right. In any case, we have our critical points. We need our fxx and fyy so that we can put these critical points into our discriminants. So fxx is the derivative of this thing with respect to x. So minus 8y, the derivative sign is cosine x. We need fyy, the derivative of fy with respect to x. I'm sorry, with respect to y. There's no y's there, huh? 0. And fxy is the derivative of negative 8 sine x. Right? So our discriminant D is equal to fxx, fyy minus fxy squared. That's going to be 0 minus 8 sine x squared. (64 sine squared x). So negative 64 sine squared x looks like it's going to be, regardless of what I put in for x, it's going to be negative, right? Because sine is going to be squared. So this is always going to be less than 0. We don't even have to put the values in. Is that what happened last time too?
So whatever value for sign you're getting out is positive, and it's multiplying by a negative.
Right. So d of pi over 2 comma 0, which is our task is to put in x is equal to pi over 2 and y is equal to 0 into d, and then that's just going to be, does it even matter? Let's just say, what? Yeah, if the origin was a critical point, but it's not, so we don't need to worry about that. So 3 pi over 2, 0, put 3 pi over 2 in for x. This is still going to be a negative number. So we got two saddle points. So I guess according to this, we don't have any max or mins, local max or mins. We just have saddle points. So let's take a look at the picture. So z is equal to 8y times cosine x So there's no max or mins, no local max mins. So let's see, what's the best view for a still picture? I don't think it'll. We can kind of see the saddle, right?
That's really just bad. Just a bad shape to take a picture of. It's kind of like you don't actually So the answers for the local maximum are just D num. Yep, D and E. Oh, you actually have to type in num. Oh, it's in D. Is half of them that are like type in num? Yeah, some have it half of them.
All right, should we try typing in the answers?
Yeah.
Oh, we need to figure out what the saddle points are. So we figured that these are saddle points. Our saddle points are here.
That's where D is equal to 0, right?
That's where, well, we have x is equal to pi over 2 and y is equal to 0. So when x is equal to pi over 2 and y is equal to 0, what does our z equal to? So z is 8, 0. Z is equal to 8 times 0 times cosine pi over 2, which is equal to 0. So x is equal to 3 pi over 2, y is equal to 0, and z is also equal to 0. Okay, so that's what we want to type in and see what happens. So DNE here, DNE here, and then now we got a couple of points. Pi over 2, comma 0, comma 0, and then another one, 3 pi over 2, comma 0, comma 0. Okay, so let's do another one. Let's try an absolute max-min. The thing about the absolute max or min is that you're kind of focused on finding the critical points, and you don't need a second derivative test. So let's briefly talk about absolute max and mins. Do you remember this thing in I don't know if you guys remember this thing in calculus called the extreme value theorem? On a closed interval with a continuous function, you are guaranteed an absolute max and min. So extreme values, you're guaranteed that you'll find an absolute max or min. So there's a lot of interesting theory about that, but let's go past the theory and just remind ourselves that in Calc 1, if you have a graph and then you closed it, you enclose it with a closed interval, you're guaranteed a global max and min. So we have a local max, we have a local min, but if you also count the endpoints, we actually have a global max, which is not the local max, it just happened to be on the endpoint, and we also have a global min. And in this particular example, the global min is the same as the local min. And if you remember the process for doing this, what we do is you find critical points. And then you find the endpoints. You don't find the endpoints, you're kind of given the endpoints. And then you put these values into the original function. I guess we put points in the original function. To find out which one's the largest and smallest. So simple three-step process, and whatever the largest and smallest values are going to be the global max and mins. So that's going to be the same idea for us if we're given a closed set. But our closed set, first of all, we're dealing with stuff in 3 dimensions, and then second of all, we're kind of restricting our values. Our endpoints aren't going to be endpoints anymore. They're actually going to be, graphs. So let's take a look at our first example, and we'll just steal the homework problem. Let's do number 6. So we have a function x squared plus y squared plus x squared y plus 5, and then we have our domain D to say that we're between -1 and 1 in the x and -1 and 1 in the y. So let's draw our domain. So D is going to be everything in here more importantly, we're also counting the boundaries. And so what we're saying here is that this graph will attain its global max and min within this boundary. So what we want to do is we want to find the critical points, because those local max and mins might possibly be also the global max and mins. But we'll also figure out what's happening in the boundaries. So let's find critical points. Yeah, so absolute value, if you remember, absolute value less than 1, less than or equal to 1. That means negative 1, less than or equal to x, less than or equal to positive 1. So that's what the absolute value means. All right, so let's find the critical points. We need fx and fy, and we need to set both of them equal to 0. So this would be 2x and then 0 plus 2xy, and then plus 0. We're going to set this equal to 0. Fy is going to be 2y plus x squared equal to 0. And so what we want to do is we want to set both of them equal to 0 at the same time. Maybe I'll make some room here. So it looks like from here I can factor out a 2x, comma 1, or parentheses, comma, not comma, 1 plus y is equal to 0. So x is equal to 0, or y is equal to negative 1. And just by substitution, maybe we'll put x equal to 0 in here and see what happens. So 2y plus 0 squared is equal to 0. We get y is equal to 0. And so when x is equal to 0, y is equal to 0. So I'm going to put that down here and put a box around it so I don't lose it. That's one of my critical points. And then now let's try to put y is equal to 1. Get 2, negative 1 in for y plus x squared is equal to 0. And let's solve for x. X is equal to positive 2. X squared is equal to positive 2. And so we got x is equal to plus or minus square root of 2. So here I've encountered two more critical points. X is equal to plus square root of 2, comma, and y is equal to 0, and negative square root of 2, y is equal to 0. Okay? Oh, negative 1? Okay, let's do that then. Okay, we good so far? Now, just one more thing to probably check before we move on. We want to make sure that they're in the domain, because if they're not in the domain, then they don't even count for us, right? They shouldn't count. So let's see if they're in the domain. 0, 0, that looks like it's in the domain. Negative square root of 2, comma, negative 1. Square root of 2, that's bigger than 1, is it? Square root of 2, 1 point something, comma, negative 1. So we got these 2 points that aren't going to, according to our problem, we're not going to need them. Because they're outside of our region D. So we can just ignore those. I would box them up, but I would probably cross them out because they're not going to account for us. So right now, the only critical point that we're going to care about is 0, 0. Well, we're going to put it in to the original function, and what we need to do is we need to compare that to more points, and so we need to find more critical values. So let's find more critical values in the endpoints. So we're going to check each of these boundaries will represent as an endpoint for us. So we got, let's see, I'm looking at this line over here. This is the line y is equal to -1 from 0, from x goes from -1 to +1. So what I want to do is I want to figure out what happens to the function when I put, let's see how I can do this, f of x comma y, where y is -1. So this is x squared plus -1 squared plus x squared times -1 plus 5. And so this simplifies to, this is an x squared, this is an x squared with a negative, so that's going to cancel. And this is a 1 plus 5 is 6. So this has a constant z value of 6. So I don't know if that was very helpful. Let's try another boundary over here. Let's try this boundary up here. This is your boundary y is equal to +1. So we'll do the same thing, f of x comma +1. And we're looking at these values between -1 and 1. So I have x squared plus +1 squared plus x squared times +1. Oops, that didn't cancel. That's too bad. Plus 5. Two x squared plus 6. So this is the function that we're looking at described by that boundary. And what we want to do is we want to find the max and mins of that boundary between -1 and 1. Right? So what we could do is we could just graph it to take a look at it, or we can do more calculus and find, the first derivative, set it equal to 0 and stuff. Yeah, we can look at it and just see the maxes in the corners. Well, we'll need to do that too to figure out these other boundaries over here. Yeah. So why don't we just graph this? So this is still vertex at 0, 6, and it goes up. Between -1 and +1, it looks like we have a minimum value here, and then it looks like it has a maximum value here. So when x is equal to 1, and positive 1 are going to be our possible maximum values. Okay? So we can conclude here max at x is equal to plus or minus 1, and then y is equal to 1 in this case. So when x is equal to plus or minus 1, should we put it in? Let's put it into the original function already. When x is equal to plus 1, y is equal to plus 1, and what's a z equal to? So 1 plus 1 plus 1 plus 5 is 8. So the same thing is going to happen when x is equal to negative 1, y is equal to plus 1, and the z value is 8. So I'm going to put 8 here and circle it, because those will just give my z values. By the way, this whole line is equal to 6. We got that already. And if we were to put x is equal to 0 here, at this point, we have a 6 there as well, right? So when x is equal to 0, when y is equal to negative 1, x is equal to 0, we get the z component to equal to 6. We didn't try 5. What happens when we put 5 in there? I mean, we didn't try 0, 0. What happens when we put 0, 0 in there? So the z component's equal to 5. So we can make a little mark over here that at this point you got a height of 5. All right. We got a critical point. We got 2 of the boundaries. Let's check the other 2 boundaries. And then the other 2 boundaries are here when x is equal to negative 1 and when x is equal to positive 1. So let's try x is equal to positive 1 or negative 1 first. So we got our function f, comma, x is negative 1, so let's replace everything with negative, let's replace all the x's with negative 1. So negative 1 squared plus y squared plus negative 1 squared times y plus 5. So this will give us y squared plus y plus 6. And then we want, by the way, this is happening when y goes from negative 1 to positive 1. So we can try to figure out the graph of this thing, or we can do calculus on it. So let's find the max and mins, or global max and mins between negative 1 and 1. Let's see, let's call it g of y equals y squared plus y plus 6. G prime of y is 2y plus 1. Set that equal to 0. Y is equal to negative 1/2. So between negative 1, x is equal to negative 1, because I want to find the local max, the critical points. So when x is equal to negative 1, I have 3 points to check. Y is equal to negative 1, y is equal to negative 1/2, and y is equal to positive 1. So I need to figure out my z values. So if I have -1 in for x, -1 in for y, and my z value is going to be what? -1. I think my z value is going to be 6. Okay. How about if it's -1, +1? Is that going to be 6 also? So x is equal to -1, y is equal to +1. What's your z component going to be equal to? 8? So -1, 1, we get 6, and then we got 8. We got those points already from before. So now what happens when we put 1/2 in for y? So basically this thing 1/2 in for y. Fractions. $5.75? 5.75? So 5.75 right here. Well, I think the global min is still 5 because 5.75 is still bigger than 5. So I think we still have a global min at a value of 5, and we still have a global max value of 8. So the positive side will give you the same values, I think. Yeah. So x is equal to 1 will give the same values. $6.75? As long as it's not less than 5 or bigger than 8, it's still, yeah. So 6. So it looks like, in general, we got a minimum of 5 and a maximum of 8. So we'll put 5 and 8. Actually, let's take a look at the graph first. So z equals x squared plus y squared plus x squared times y plus 5. And then let's actually use the same limits since they have square limits over there. It's going to go from -1 to 1. So this is what we're seeing. Let's take it up a little bit. It starts at 5 to 8. Oops. So let's see if this matches our description. We have a low value at 0, 0. We got, if you look at the front here, it looks like it's constant. That line has a constant ridge of 6. So this thing dropped down to 5.75. And then this thing went down as low as 6 also. So I think all the pieces are there so that we can examine this and confirm what we found. So let's take a picture of it and let's put it on a new page so we can actually get all the pieces. Again, we have 0, 0, 0. So this line over here has a z-value height of 6, and it's constant. We got the maximum values here at 8. What were the x and the y values again? -1, 1, 8, and then the x values here, +1, 1, and 8, right? We found a couple of other interesting points. We found a little minimum over here, local, with respect to one of our graphs. And this was -1, -1/2, 5.75. So -1, -1/2, and 5.75. Oh, by the way, this is 5 here, 0, 0, 5. And then we found another dip over here. Remember that other dip over here? I think that was a 0, +1, and a height of 6. It's a 0, +1, and a height of 6. Okay? So we're using the boundaries to help find more potential max and mins. And unlike the stuff that we used to do back in Calc 1 where we just check the endpoints, we got 2 endpoints and then we're done. The boundaries for something that's two-dimensional could be as many as 4, 5, or 6 sides. Or sometimes we might get lucky and might actually just be one graph like a circle, in which case it might be easy to check that way as well. So in this case, we found our absolute max and absolute min. So it looks like our absolute min was absolute maximum value was 8. The absolute minimum value was 5. Okay, so the next one is a little bit easier because instead of 4 sides like we did, we have x is bigger than 0, y is bigger than 0. We're going to have 3 sides. A little easier. So let's just take a look at this without having to do this. The major steps are to find the critical values and then find the boundaries and then take a look at the graphs of the boundaries. So let's see if we can run through this in a couple of minutes without actually doing it. And what's important is to identify your boundaries. So your boundary here is x and y values where x is bigger than 0, y is bigger than 0, x squared plus y squared is less than or equal to 3. So I think you have a circle, a radius square root of 3, right? And then so that's one boundary, and then the other 2 sides are here. We got y equals 0. And then we have another boundary over here. That's x equals 0. And then here you just need to plug in your function. X squared plus y squared is equal to 3. And then what you might want to do is either solve for x squared or y squared and put it back into the function to figure out what's going on there. Okay? So if I'm looking at this function, I see there's a y squared over here, so I probably want to solve for y squared and replace it with, so f of xy equals xy squared plus 6. So I'm probably going to want to replace this with y squared over here. So I'll have f of x comma, and then the y, I'll change the y. So I'll replace that, and now I just have a function of x, and I'll find the max and mins that way. This one over here, we have vertices -2, 3, 2, 3, 2, 2, and -2, -2. Well, that sucks. So this one is trickier because now your sides, you have 4 sides, and then you have 3 sides that you can express with either x is equal to something or y is equal to something. And then now you have this side over here that you need to write as an equation of the line. Probably y is equal to x. So you'll need to express those with those different values, put that into the function, and then find your max and mins on the boundaries that way. All right? All right, so it looks like we're out of time, which means now we're going to be 2 lections behind. Your quiz on Thursday will be on second derivative test, which includes finding critical points. And then finding the local max and mins.
So what is the purpose of the second derivative?